going. All right, hopefully, you should be here for EME. Oh, I'm not sure how I should take that snippet. I won't take it personally. I'm a big boy. All right, so it should record. So any of you who've taken undergraduate class with me, well, actually, if you looked online, you'll see that we do screen captures of things. Leave that. I don't want to disturb people across the hallway. And so I will post this after we had this conversation. But this class is EGEE 521. Oh, I did change. Or is it 520? It will be EG 521, and then it will be EME 521. It's a class that has in some way or form been taught here for definitely longer than you've been live. I think the first offering of this might have been 1986 when I first arrived here in some form, but it's evolved since then. I know you say, you don't look that old. You look so beautiful. But it's true. And so this used to be my modeling class, and still is kind of my modeling class, but it's also taken on this mantra of being one of the, is it 5 core classes in energy and engineering that satisfies the general graduate education thing. So the first time I think that probably it's been offered in that mode, and it's because the program has only been revised in that way recently, and so it's not changed from previous versions. But what it is it's an online class in computational methods. It's not a standard numerical methods technique in a broad sense, but it's for distributed systems in that it looks at spatially solving PDEs for solid mechanics, flow, fluid transport, heat transport, mass transport, and Navier-Stokes flow, using basically finite element methods individually for those systems, but then also coupling them together for coupled flow deformation systems. And so that's kind of the topical area. And I did make case notes of what I want to talk about. But in general, the class is online. So for better or worse, this is almost the last time you'll see me in this class. It's all prosecuted almost at your desired pace. It's kind of on a weekly pace, as you'll see as we go through stuff. And it's a bit what I would call loosey-goosey in terms of the evaluation. So the evaluation for this is identified further down the page. The scoring, hopefully it's right. Actually, does it not have it on there, or did I miss it at the top? Did I remove that? Well, it'd be good if we knew what our grades are all about. The grades are basically, I thought it was on there, but the grades are basically 50% of the grade is for doing some online assignments. They're basically MATLAB programming exercises. I won't take them in, I won't check them, but you will check a box to say that you've completed them. And so that's on the honor system. And the other 50% is to work in a group to give a presentation sometime probably in the week of April the 11th, close to the end of this class, on a topic relevant to the topical area. And so I will ask you at the end of the class, I'll send out an email, ask you to rank in rank order the first, second, and third, the topics that you might want to talk about, of which we'll talk about what those topics are in a second. And I'll gather those and try and put you in groups of like minds, or maybe if you have friends in the class, you'll choose what the topics are that you want in the same rank order, with the expectation that you might end up in the same group. So it depends what you want to do. So it's, I think, a relatively straightforward class in terms of what we talk about. So it's really talking about mechanical deformation, transports of fluids, mass, and heat in media, continua typically, And I guess in addition to that, Navier-Stokes flow for where momentum is important, which is kind of a bit of an orphan in there. And then taking those four systems, mechanical deformation, fluid flow, mass transport, and heat transport, and looking at ways at which they can be combined in some way. And all using domain-related methods, the finite element method in actuality. And so all of the material is online. And so hold your Snickers. Oh, I didn't have to go back to it. So if you want to find the resource page that gets us here, I guess it's marked in here, but the copy you have is probably so poor that you might not be able to find it. This resource page you can find by finding me. So if you can find me and search on me. So 10 years from now, you'll be having kids. That's probably right. 20 now, 30, that's the normal time when people have kids. Give your kids unique names so that when they search themselves on Google, they will find themselves and not have to scrap around. That's my only advice to you. So this class, the resource page is online here. And everything that you need is served to you from here. The syllabus, which we just looked at, is online, which describes our first meeting, which is now. That's online only. It's 3 credits. The online materials at the resource page, it says a little bit about what you'll do, and then it just gives a syllabus for the fact that we'll talk about these systems for mass and energy transfer traveling by diffusion, which is the same as Darcy's law and Fick's law and Fourier's law, are all diffusive processes, which allow us to look at those 3 systems for fluid flow, mass transfer, and heat transfer, all using one set of expressions. And then, in addition to looking at conductive and diffusive flows, we'll also look at advective flows, where they're transported by the agent of another carrier fluid. So if you have water flowing within the subsurface, it's able to not only conduct heat within that water, but also physically move the heat along by advection. And the systems of equations that we use will be related to that. As I say, we'll talk about this orphan child, which is momentum transfer for Navier-Stokes equations, I think in one lecture. It's not really a central part of what we will do. And then we'll talk about solid mechanics. So the actions of deforming things and how you calculate how things will deform, where the constitutive law, instead of Darcy's law for fluid flow, Fourier's law for heat flow, and Fick's law for mass transfer, will be Hooke's law, which links strains to stresses within the system. So all this will become clear as you look at it through the lectures. Everything is served to you online, so you can do this in the comfort of your... I didn't want to go there, but I'll go there in a second. Everything is served to you. And so the course notes are online and can be downloaded. I think they're not pretty, but they're moderately functional, and you'll see how you can use those as you go through this. The prior classes have been recorded for your convenience, and you can either access them on YouTube like this, where they're set up, or perhaps more conveniently, you can access them through this webpage. So this is EGE5 something. It's called by a variety of names, I think. So you get the picture. And so these are things that you'll end up looking at, typically 2 per week on a Tuesday, nominally on a Tuesday or a Thursday. And if we look, I'm surprised that in the syllabus I don't have either. Has it got cut off in some of the things? Oh yeah, so I'm not sure what that other syllabus was. So these are basically, you'll probably be interested to know how your what the deliverables are. So deliverables are pretty straightforward. They're these programming assignments using MATLAB. The MATLAB code is a code that I wrote, I'm guessing, more than a decade, a decade ago, which is a finite element code, which is bare bones. It's not a commercial code, but it's something that you have to go into and play around with to be able to do the assignments. And you'll solve problems for elements that are one-dimensional or two-dimensional that are for solid mechanics or these different kinds of flows, advective or diffusive flows, and also coupled systems. And you'll tick off on the fact that you've done those. I won't check it, but you should do it. And then the one thing that we will meet for is in the week of April 11th. I'll send you an email asking you to rank in order, either the first three or all of them, which one you'd prefer to work on. And you will end up making a presentation as a teaching presentation. So all of the lectures that are recorded on YouTube are tutorials, if you like. So they're not presentations, I think, that you'd get at a professional meeting because they go at a different pace, but they have very specific components in them to introduce why you might do this, introduce the governing equations, maybe derive them, solve those governing equations in some way, typically to do a hand example, hand solution, to be able to solve it, to be able to demonstrate straightforwardly the mechanism by which it's done, and then come to some fine conclusion that includes perhaps videos of these methods that have been applied by other people to much more sophisticated systems. So as a group of probably, if we have 20 people here, and if we do 4 of these, there'll be groups of 5 or 4, depending on how we choose to split it up. And these would be methods that really aren't covered in the class. Smooth particle hydrodynamics is a method for fluid flow, a meshless method for fluid flow. Lattice-Boltzmann methods are methods that are used to represent Navier-Stokes equations for flow in porous capillaries, where it's almost at a molecular scale that you're evaluating these. Phase field methods are methods to be able to substitute variables, to be able to look for inclusions and inhomogeneities, and for fractures in different systems. The extended finite element method is a way of including fractures for fluid-driven hydraulic fractures, for example, into finite element methods. Boundary element methods, as you'll see from the other notes, are ways of solving continuum problems where you, instead of discretizing throughout the volume of your system, you only put elements on the outside boundary of the system. And so it's quite efficient because you end up with less equations to solve, but it's typically linear rather than nonlinear. And discrete elements are granular mechanics models where you take a bunch of particles, grains of sand, that can rub up against each other, and you solve Newton's second law for their interaction through F equals ma to be able to solve for how the arrangements of those grains of sands develop. So there are really only two deliverables. The things that you do yourself and attest to the fact that you've done them, and the things that will be part of a presentation, and we'll view those in the week of April the 11th. So that's kind of where we are with that. Some resources from the library. This is the material that's online that you can get. I'm not sure that you need to go to these other things. There are a couple of things. I think of both of Zenkovich's book as kind of the finite element Bible. Quite an involved book, but I don't think you need those per se. Academic conduct is that certainly if you attest to doing things, you should have done them, even though I will not check on you that that is the case. So that's kind of the outline. There is a small finite element code that I wrote. It's called EGE-FEM. You can download it. It's, if I go and find it, it's in a zip file. If I unzip it, you can do the same. You'll find out that, I'm not sure if I can, these are MATLAB files, which I will open with TextEdit, I guess. And all you'll see is, I guess I could probably make this a bit bigger. Well, that's interesting. It's bigger on my screen, but it's not bigger on there. That's not very useful. Well, you can see a bunch of MATLAB commands. You can't see them very well, perhaps. And I don't know how to. Maybe I can change the font in this. Is there a format? Bigger. Oh, that's even better. Plus one. Fine. So you get at least some semblance of what's going on there. So it's a very simple program. It reads some different input files, and then it does something with those files to be able to get some output. And so the finite element method, which is really the focus of this class, is one that has a core program that does some things like solve equations. Well, first of all, takes some input data. It takes that input data, which would be things like the nodal coordinates of nodes that make up a mesh. It would take some material properties, use that input data then to assemble a system of equations. And it does that by isolating nodes that are close to each other and describing them by individual elements. And for those elements, it calculates what the stiffness matrices are, or the linking matrices are. And the reason that it's able to, for instance, do flow problems and solid mechanics problems and Navier-Stokes problems is that this element, the subroutine that controls the equations that come out of this subroutine that describe the element, are different for flow problems or for deformation problems. And so one program, like this one here, EGEFEM, is able to solve these solid mechanics and flow problems only by changing the nature of the subroutines. And the subroutine might be something which is, well, I'll show you one of the subroutines blown up, the one that we'll look at. In the library, this is open with text edit. Again, it's small. But if I make it bigger, so this would be typically one of the things that you'd have to mention. This is done. This is a solved problem. This is your first assignment done. So it's in there, done, but there's also a stripped down version of the code that doesn't have this in that will challenge you. And so I would encourage you to use the one that's not stripped down. But basically this is something that takes in some information from an individual element. So it's a one-dimensional element with a node at each end. It takes in the x-coordinates of the two ends of that element. It uses those, it zeroes out the individual elements that you'd like to calculate. This is the matrix that it sends back to the main program once it's figured out what it is. And all it does is it uses the permeability or the conductivity of that material. It uses the cross-sectional area. So an element from two nodes, one to the other, has a cross-sectional area. And it has a capacitance, a storage term if you like. And to be able to do the calculations, it needs to make a matrix which is equal to this area multiplied by conductivity divided by the length of the element, simply what it is. So it does this calculation for this coefficient, and then it makes a 2 by 2 matrix, which it then sends back to the rest of the code. And so the idea is, for a one-dimensional matrix element with two nodes at one end for flow, the part that makes it perform in the way it does is this 15 lines. If you want to have a two-dimensional element, then all of a sudden it's more difficult than this. It's a bit different. But basically, you have some information that comes in terms of the geometry, the material properties, and you zero out a matrix, you calculate some terms, and then you send it back to the main program, and it does the rest of the calculations for it. And so the one strength of some of these numerical methods, which have been around since the late 1950s, the earliest finite element program was 1958 with Wayne Clough, not for geological problems, which is what I work in, but for flight structures. And so these have been around, and since that time, and there are very versatile ways to be able to solve all kinds of physical problems that you might want to solve. So anyway, we digress. That's probably more information than I needed to talk about. So coming out of this, I guess it's blown this up as well. So if you look at the material that's available to you online, this is the program we just downloaded, and I opened up from the unzipped file. There's one which is incomplete. So this is one where I'm pretty sure that if we look at the individual elements, where will that open? If I look at the, you can't see this and I can't make it bigger. I'm trying to, yeah, how does it open? Open with. No, actually that's not stripped down either. So I'm kind of curious as to whether, hopefully I'm opening the right one. Yeah, okay, this is it. So something like this. So this is a similar relationship. So it says that you need to transfer something to get here. Well, this is just as we looked at before. But now you have to figure out exactly where in the data file these things of conductance, area, and capacitance are, and what you have to do once you get it. So the incomplete one is incomplete, as this would suggest. But I think the backup one is complete, and so I would admonish you to use the incomplete one, but the other resources are there as well. You know, part of the rationale for this is that I don't, maybe I'm a bit glib about this, is that I look on this as a tools class. It's not a qualifying class per se, right, for the major. If you're taking it in the EME program, it's not a qualifying class per se, but it's a tools class to give you some tools that you might want to use in the work that you do here as a grad student to be able to be more efficient and effective in what you do. And so from that point of view, I think you need to decide exactly how you want to prosecute this for yourself. You should want to, you need to shed all these ideas of, geez, grades, this, that, and the other. In graduate school, I don't think it matters. My first semester in graduate school, I got a C. I didn't realize, of course, coming to America, that actually a C in graduate school is a failure. but yeah, you're here to learn. You're here to learn something. You want to broaden your skills and broaden your mind. And I think there's hopefully enough here to do this. So there's this full code. There's the incomplete code as we looked at on the screen. There's a key which is basically lays out the assignments for you. And I'm not sure I can get it all on at the same time. But if you look at this, this is where we are today. Tuesday, Thursday, we're meeting. So really it kicks off I think they might not come live until the Tuesday when they open. Yeah, that's probably a good way to do it. But for each Tuesday and Thursday, there's some kind of online lecture with hopefully some pearls of wisdom within it. And then once you get to the probably the Thursday of week 3, so this is week 1, 2, 3, there's a problem. This is exactly the element we looked at that's already done. This is the input file. And so the coding on this is that the main code is this big MATLAB file. And it borrows two things. It borrows an element subroutine, which does the calculations with the data that come localized into that particular place. And this is all online, so you don't have to take this in now. And it also uses an input file. So it uses these two components. The input file gives the coordinates and where the elements are relative to each other for the geometry that you're using. And is specific to a particular kind of problem, flow, transport, or solid mechanics. And the element subroutine is the appropriate one which will be grabbed automatically because it's defined in the input file. But you'll notice that these numbers correspond to each other. So that the secret coding here is that in all of these, the first digit represents the dimensionality of the problem. So this is one dimension, two dimensions, two-dimensional, two-dimensional. So the elements that we're talking about in one dimension are usually just a stick with a node at each end, which would represent flow along a pipe, if you like. And the elements in two dimensions would typically be triangular elements. So a node at each vertex fills an area rather than just a length. So it's two-dimensional, right? X, Y, and it fills, I know this is a bit hokey doing this, but I'm not going to write on this. So these are all triangular elements that define these. And we'll talk about these in the lectures. And the second digit represents the kind of physical process that we're representing. So one represents flow, either fluid flow or heat flow or mass or diffusion. They're all the same equation. Fick's law, Fourier's law, or Darcy's law. Two represents advection, where there's not only diffusion in the water by Fick's law, but also it's advected by the motion of a fluid and carried downstream. Navier-Stokes, in this case, is where inertia is important. Actually, we don't include inertia in the solution we have, but it's Stokes flow, I think, which is 3. And for solid mechanics, using deformation, it's 4. So by the time you go through this, you'll talk about behaviors for each of these classes of physical systems. And then 5 is where we linked fluid flow and deformation together. So it's like compressing, well, like consolidation of porous medium or subsidence of a reservoir. You have a sponge, think of a sponge. If you take that sponge and it's full of water, then you can apply a deformation to it. As you apply a deformation to it, you'll squeeze water out of it. And it's no different from a porous medium doing the same thing. And so to be able to represent that, you'll already have talked about flow problems earlier. You'll already have talked about mechanical deformation problems. So those are two separate sets of behaviors that you could have deformation of this sponge and you can have flow in this sponge. And you can analyze the sponge for those systems without those two processes communicating to each other. But you can also link them so that the deformation that you get will compress the fluid, it will raise the pressure. The pressure that's raised will force it to try and get out of the sponge, and therefore incrementally you can link them together to be able to accommodate these coupled systems. So that's right. So my goal here is not really to introduce the science of what we're talking about, but more to introduce the operational activities that you'll be involved in. So the things we talked about are summarized here. The fact that the first digit is it should be 1, of course, right? As one-dimensional, so this should be 1, 2, not 2, 2. And the second digit refers to flow and diffusion. This is advection. This is Stokes flow, not Navier-Stokes flow. This is solid mechanics, and this is solid mechanics and conductivity coupled together. So, it's a class that in these 30 years has been taken by people kind of across the spectrum, from other locations in the college, from geosciences to math to people in this department. It's a class that the students working with me typically take. This is an introduction to some of the things that we do in our group and beyond. And so I don't think you'll have problems with it. But if you are concerned or curious about the material that's in there, I think all of this stuff is actually served online. I'm trying to think what we haven't been through yet. Getting smaller. Okay, so you have the materials online, you have EG, FEM, you have the incomplete one, you have a key, which we just had on the board. The presentation, as I mentioned, are these, well, it's now 7 topics, I guess, on this, relative to what we had before. So I'll send an email asking you to respond with your rank list of what you might be interested in dealing with from this list of 7. If you want to work with someone, then you know how you can physically make that happen, I think, right? Just by having a common ranked list. But basically the idea, as you look through these individual Tuesday, Thursday presentations, you'll see that they all have these kinds of components. And this is what I just mentioned earlier. And so this will be the relatively loose grading on the presentations that you'll do. And that is, you need to introduce the topic. What's the topic do? Why is this topic, this numerical method available? What are its characteristics? When does it work well? When does it work poorly? What does it look like? When was it developed historically? What are the general equations or principles that describe its behavior? How can we cast that into some governing equations that describe it? As you look at these presentations that I give, almost always there's a hand-worked example of putting some numbers in some equations to be able to show exactly physically what it is. And that's useful because if you are coding things in MATLAB, which you will be, the computer adage is garbage in, garbage out. So if you don't check what your results are, that they make sense, then they don't make sense, right? And so you have to be able to do that. So hand calculation and confirming that with something that you do in MATLAB is probably a useful thing to do. And when it doesn't give you the answers that make sense, then you have to kind of dissect it in some way. And so to me, this is an important thing in the education process in understanding how some of these things work. A numerical example, done somehow, maybe using some software or maybe not. People have done this in different ways. And some examples from what people have published, some videos solving fancy problems, much fancier than we do in this class, to be able to round it out. And so that's kind of the evaluation for these presentations. I'm a generous guy, as it turns out, just because it's sometimes easier to be generous than not be generous. So you need to take this seriously and actually enjoy it. But as I say, it's a tools class, and hopefully you want to do this because you want to learn about these things, not because you have to do it because someone told you had to come here or because you have to get through some kind of qualifying exam. And so that's my hope for this, because this has been my life, right? As you can imagine, for not a significant, an insignificant component of it. Peer review as well, which we've never usually had problems with that. I'm not sure actually whether we've physically done that. We're not leaving you completely in the lurch. This is when, this course was taught in this form in early 2005 for the first time. The presentations over the last little while, I think, are here. Just the PDF files by the looks of it. So you're not completely left in the lurch. I'm trying to think what the best one I ever thought was. It was XFEM. Is it on there? Yeah. Bet you this one. This is the best. This is it. This is Alinium Pour. This is the one that I thought was the best. Not necessarily because it was any more involved, perhaps because it was less involved, because it was much more tutorial. It dissected things and put them in a form that within an hour and 15-minute period, which is this, right, 75-minute periods, could be completely digested, I thought, by the audience and understood. Very different modalities from the talk you'd give at AGU or SPE meeting, which is fast and furious, a few results that come out of it. Don't need to go through all the equations because everyone's seen those before who are in this technical area. But in a tutorial sense, it's something that you have to lay out and take through step by step at a pace that people can, your colleagues can understand. And so I thought this one is the one that sticks out in my mind as being a nice presentation. One that I thought was quite nicely tutorial. What else? Don't know why that won't be any bigger. I could do the XFEM stuff, but it's tough to do. So I don't know, to be able to do the coding, you probably need access to MATLAB. I don't use MATLAB. I use a code called FreeMat, F-R-E-E-M-A-T, which is a Mac free deliverable that does MATLAB. which is actually quite useful. And I guess I have it open. Do I have it open? Yeah, this is what it looks like. So this is what it looks like. So if I know you can't see this very well, but this is that one-dimensional. Let me see if I can. It's very curious. So my screen gets very big, but this stays the same on the overhead. But this is just a code that if I run this, if you look at this background here, I think I can clean this off actually. How do I get rid of this? I'm trying to think how to. Don't know. Well, yeah, anyway, so you can see it's looking for things 1 plus 1. So it's just like MATLAB in that regard, but that also allows you to batch execute. So I can run this finite element code with this particular input file, and it will automatically use this particular element. And if I do that and you look down here, then you should see that it executes. Well, it doesn't execute. This will execute. And it gives this number here, which says that it actually corresponds. You see this is 20, 23.33, and 25. And this is 3.3 times 10 to the 6. Perhaps you can't see that. But if you look into, I don't know if I can make this small. It doesn't want to go small again. If you look at the notes, which the course, of course, follows, then there's an example in here for flow. You'll see that they're kind of rough and ready, but these are the ones that I use in the recorded presentations, and they actually, I think, make sense, but you might decide to disagree with that. I'm looking for this first example. I made the case that it's important to be able to do hand calculations to be able to demonstrate exactly what's going on. I think it's a useful tutorial trick. This is some MATLAB. MATLAB fluid flow. So, it's all very straight. There are not many things I can do in life, but there's one thing I think I can do, is I think I can explain the stuff that is zipping past you. So this is an example for flow. And the question is, if you had a dam that looked like this, with an upstream water level, a downstream water level, and you wanted to calculate how quickly does stuff go through it, how'd you do that? Well, what you could do, you could divide it into 2 elements. One element here with 2 nodes, one element here with 2 nodes, and you could physically solve that problem by hand. It would be a 3 equation system by dividing it up first into the individual elements and then solving it. And if you go through it and get the solution is exactly this. Is that this upstream head is 25 meters. This downstream head is 20 meters. These are 2 different materials with different conductivities. The question is, if they're the same conductivities, the head at this point would be exactly the intermediate of those, 22.5. But if this one is more permeable than this one, then most of the head loss will be here. So the head here should be higher than this middle bar. It should be higher than 22.5. And so you can go and calculate that. And it turns out, if you do the calculation, it turns out that it's equal to 70 over 3, which is 23.33. So this is 23.33 as this intermediate head, 25 upstream, 20 downstream, and 23.3 in the middle. And if you look at the flow rates from upstream into the system and downstream out of the system, they have to be the same if it's steady state. And those flow rates end up being 3.3 times 10 to the minus 6 meters cubed per second. And again, maybe you can't see this. Maybe you can. Your eyes might be better than mine. So these are the final results from this just simple, very simple code. Upstream 25 meters, downstream 20 meters, intermediate 70 on 3. And the fluxes from the downstream element, upstream element, and the middle element, same amount comes into that node as leaves it, so zero accumulation. And these are the negative of each other because in steady state, the same amount has to go in as goes out. And so even with a very, very simple code that has these simple element subroutines, you'll be able to explore and have some fun doing this. And so to make it not so Mickey Mouse, the other component of this is that the techniques that we use to solve for these equations are exactly the same techniques that are in ANSYS and ADINA and COMSOL that you can buy for $10,000 or $15,000 or use from the central computing stuff on campus. Exactly the same techniques. Same method of taking data in, same method of parsing that data between nodes and elements and storing material properties, same way of building element subroutines, same way of solving them, kicking out the results, and also the same way of combining different material behaviors like flow and deformation with each other so they are either uncoupled in some cases or if you want to, they're coupled. So, yeah. Questions? Was that fast enough for you? Go ahead.
Are you uploading more videos or do we have all videos
Everything's
and
there.
material?
Everything's
Okay. So no new videos. And this checkbox that we
It's on quiz. It's on Kansas, yeah. Good.
on
Good.
Canvas?
Canvas, yes. Yeah, good question. I'll bring that up. I didn't do that. So, Canvas. So if you're here, you must have got an email from me, right, as an announcement, right? I presume. And so if you go into your Canvas account, this is it. You can do a student view, I guess. And so this is what you should see. I don't know where that went. Yeah, so you should. So let's see. These are the assignments. Okay, perhaps I didn't make one. So the assignments, upcoming assignments. So, develop and implement, can you see that? Develop and implement an element subroutine, blah, blah, for various geometries. Take the quiz for steady flow. Did you do it? Perfect. So don't abuse it, of course, I know you won't. But also, so each week, I guess it's not live yet. So leave student view. I'll look at what I see in this, which is different. And so each week you'll get an announcement. You got one already. And that announcement will tell you what you need to do. And they're all timed. So week 2 deliverables is next week. So what you want to do is, this is the study guide, I think, this is the booklet, which has 300 pages. So you can either go directly to YouTube to do it, YouTube. So this is EGE 520. It's called these charismatic videos, you know. Do you think the Golden Globes or something should be honoring these or something? Yeah, so you'll see it. They're screen captures, just as I will have captured on this. Or you, I think, can open them up in a small window and a big window.
This allows you to solve nonlinear problems.
So they are tutorial. Some scribbling, maybe not always pretty, but you can rewind them if you wish to, or not. And they're also not on Canvas. There's really only one of these, but if you want to look around elsewhere, for instance, I don't know how to stop this now, but if you want to go back to the course resources page, then there are multiple ones. So this one's 2015, this is probably 2016, I'm guessing, I'm not sure. They'd be similar to each other, but not identical, because I'm only so creative. And you see a date, 2016, January the 15th, 2016. And so there's lots of resources. So these are the same. There's a tutorial in there. I can't remember what that is. But anyway.
We've basically said that we can...
Should be careful of the stuff on the side, right? You can see all the junk I've been watching, like fails of the century at midnight for entertainment. Yeah, so you see it. So it's all laid out, I think, quite logically. So that's it. So I would encourage you that if this material interests you, you should do this. If you're doing it as a kind of qualifier thing to get through it, and don't think you'll use it and stuff, then maybe it's not the deal for you. It's obviously up to you. We had 20, 1, 2, 3, 4, 5, 6, 7, 8, 21 online. So I won't bring up the screen with people's names. So I will send an email around. Things will start, I guess, on Tuesday. And so I guess that's after the drop-out period. Certainly you can look at this stuff beforehand to see if it's something that you're interested in. The reason for not sending the email around straight away is that some people may drop and some people may add. No, I'll send it around anyway, because then I won't make the groups until after that drop-out. And so if you want to work with someone in particular, you know how to engineer that. Any other questions? How many views? 400 and some thousand?
Wow.
Well, it's been there for a long time. That's not very many. So, where's YouTube? Does that buy me some street cred?
You should see if you get some ads.
No, we always talked about that. If you get ads, you can monetize it, but you get ads. And 410,871, and does it say how? I thought it did say. Oh, I thought it said on the same page how many subscribers you had. 3,000. Yeah. So you can join. Get your friends to join. It's engaging stuff.
We can be the class that gets you to 3,000.
There you go. I want to get 500,000 views. Work on the views. Yeah, the views right now are 410. So yeah, I think it's a cool way. I think it's a cool way to present stuff. So my rationale on this, on doing this, you could probably do this for the university, is that this way I actually control and own this, right? For you as well, intellectual property, your intellectual property is what will be your livelihood, I think, right? You're training in a technical, scientific area, and so it's your ideas and your way of thinking. The university has this content, they don't need me anymore. I'm not going to be here anymore because you're going to be doing it on your own. So having it in this way, I think, is kind of interesting. It's interesting, actually, to think about what education will be in university education will be in 5 or 10 years' time, with disruptive technology, etc. So this is the beginning of disruptive technology. So things will definitely be different 5 years, half a decade from now. Anything else? Open door policy. I'm sure you can work this out for yourselves. But open door policy, afternoons are best for me. I'm less grumpy in the afternoons. Mornings are for getting stuff done, right? Sometimes the door closed. And afternoons, just to chat. If you want to come and chat, it's kind of fun to chat as well, just with people. Not necessarily with a question about this, but just to shoot the breeze. That's kind of fun too.